Hello everyone, welcome to lesson 1.3. What are we going to learn about? Uncertainty. So if you don't know what's going on, this is the lesson you'll understand because it's about uncertainty. Okay? And we're talking specifically about uncertainty in measurements. Because in physics often we take measurements and we need to have a clear idea of how precise we are measuring something. Okay? How certain we are of our measurements. So, you're on your way to school, and a police officer measures your velocity at 1,930 kilometers per hour. But how accurate is their reading really? So, is it exactly that? Is it about that? Are there more decimals? Is it 1,930.4? Or maybe it's way lower. So there's uncertainty there. And there are two main things we're talking about with certainty. So there's accuracy and precision. So accuracy is a description of how close a measurement is to the real or accepted value. So if we've got a chunk of metal and we know that it is exactly 1 kilogram, and you put it on a scale and it reads 0.999 kilograms. So 999 grams. That's pretty accurate. Okay? If you have a mass of 75 kilograms and a scale consistently measures you at a mass of about 75 kilograms, then it is accurate. Okay? If it reads 130, that's not accurate. Okay? So accuracy, pretty easy to figure out. Precision. Precision is a description of the degree of exactness of a measurement. Okay? So a ruler that can measure to the nearest millimeter is much more precise than a ruler that can measure to the nearest centimeter. Okay? So the one that can measure to smaller amounts is going to be more precise. Okay? It's good to remember, though, just because a device is accurate does not mean it is precise. Okay, a bathroom scale that accurately tells you that you are 75 kilograms, okay, that's accurate, you're 75 kilograms, that's not very precise. It doesn't tell you any decimal places. Maybe you are 75.2 kilograms, okay? So you would never use a scale like that to measure a tablespoon of sugar, okay? Because it's not going to measure those tiny amounts, okay? And just because a device is precise does not mean it is accurate, okay? So a scale that can measure to the nearest milligram is very precise, but if it's slightly broken, it might not be very accurate. So it might give you a mass of 72.358 kilograms. Wow, that is precise. But that's not very accurate if you are actually 75 kilograms. Okay, so it's measuring to 3 decimal places, but it's not all that close. Okay, you are not 72.358, you are 75. Okay. Check out this clock. How is its accuracy and how is its precision? I'm doing this at home, so I'm using a clock. Yeah. Okay. Hopefully you can see that. Yeah. Whoa. Okay. So, how is its accuracy? Well, it's reading 851. Okay, now that's actually not very accurate because it's later than that. Okay, so it's not very accurate. How precise is it? Well, oh my, this is hard. 851. It might be 851, but is it exactly 851 or is it 851.30? Is that what it is? So it's a beautiful clock. It hangs nicely on the wall, but it's not very accurate right now. And it's not very precise either, right? Because we don't know to the nearest second or millisecond, etc. Does that make sense? Sorry. Okay. So, instruments are going to have a certain amount of uncertainty to them. Okay, so an instrument is going to have a certain amount of inaccuracy, right? Because it's probably not exactly on, and it also might not be very precise. There's another type of uncertainty when we're doing physics, and that is experimenter uncertainty. So you and I are not perfect. We make mistakes. Okay? So there's instrumental uncertainty and there's also experimenter uncertainty. And when you're doing an experiment, you need to know to what degree you are causing uncertainty. Okay? So, for analog instruments, like a clock like this, okay, there can be disagreement about the results. So this clock here says 9:22, or is that maybe 9:21 and a half? Okay. Digital instruments, we can be there's not going to be disagreement, but analog instruments, there's going to be uncertainty about how we read them. Okay. So another thing that we need to talk about is significant digits, and you have some experience with that, sig figs. Okay. And this is very important because it tells us what degree we are sure about our measurements. Okay? And there are certain rules that govern sig figs. Okay? So sig figs are the digits in a measurement that are valid. So what is the length of this blue block? Okay, well, according to the top ruler, it's 6.6 centimeters. According to the bottom one, it is, let's see, 6.1, 2, 3, 4, 5, 6, 6.6. Well, it goes maybe a little bit past there. 6.62? Okay, now, I think that's pretty true. Would I be able to tell from the top one that is 6.62? No. Okay, so according to the top one, it's about 6.6. According to the bottom ruler, it's about 6.62. Okay, we have more certainty about this 6.6 from the bottom one. Okay, from the top ruler, I think it's about 6.6, but someone else might look at this and be like, are you kidding me? That is clearly 6.7. So there's uncertainty around this digit, but not really with this ruler. Okay? So the uncertain digit in the top ruler is that 0.6. The uncertain digit in the bottom ruler is that 0.02. Okay? Okay. If something is measured as 1,500 kilometers, okay, so someone tells you it's from here to there is 1,500 kilometers. From here to Chilliwack. I drive the bus every day. It's 1,500 kilometers. Okay? How precise is this? Is it exactly 1,500 kilometers or is it roughly 1,500 kilometers? So those zeros at the end, are they actually measured amounts or is someone kind of rounding? Okay, with those zeros, it's not entirely clear because we often do that. We round things when we give people a measurement. So there are rules for determining the number of sig figs. Okay, rule number 1: non-zero digits are always significant. So if the digit, the number, is not a zero, it's significant. So for example, 1,500 has a 1 and a 5. Those are not zeros, so those two are definitely significant digits. Okay. Number 2, all final zeros after a decimal point are significant. Okay, so let's say we've got a measurement of 3.0 meters. That 0.0 is a final digit. It's the last one in the number, 3.0, and it's after the decimal, therefore it is significant. Rule number 3. Zeros between other significant digits are significant. So if you've got a 0 in between two other digits that are significant, it is also significant. So let's say we've got 101. Okay, something is measured as 101 kilograms. Okay, the ones are significant, and the 0 right there is between them, so it's also significant. Okay, and the final rule, number 4, zeros used only as placeholders are not significant. Okay, so 1500, we say that those zeros are just placeholders. They are telling us that we're dealing with not ones and tens, but hundreds and thousands as well. Okay, so let's try some examples. Let's see here. Oh my. How many sig figs in 0.0035 meters? Okay, well, the 3 and the 5 are significant. This 0 is not a final 0. It is after the decimal, but it's not a final 0. If it was over here, it would be significant. But these ones are basically placeholders. Okay, I'm going to go back up here. They're placeholders. So they are not significant, so the answer is 2. Just the 3 and the 5. Okay, I could rewrite that as 3.5 times 10 to the negative 3. Okay, right? 1, 2, 3. So 3.5 times 10 to the negative 3. Okay, what about 2.007 kilograms? Okay, well, the 2 and the 7 are significant. Okay, and these zeros are between other significant digits. Okay, so they're significant, so we have 4 sig figs. All right, 1,805 milliliters. What is your guess? That's right, it is 4. Okay, 1, 8, and 5 are significant. The 0 here is between them. Okay, oh dear, 3.020. Put in your guesses. How many sig figs in 3.020? Well, we know the 3 and the 2 are significant. We know this one's significant because it is a final 0 after the decimal point. And we know this one's significant because it is between 2 sig figs. So this one also has 4. This one, 3. Okay, the 3 is significant. The 0 here is a final 0 after the decimal place. And the middle one is between 2 sig figs. Yeah? So, significant digits, there are some typical situations where zeros are not significant. So, 15,900 kilometers. Okay, that is a typical situation where the zeros are not significant. The zeros could be measured, we just don't know for sure. So if someone tells you that from here to Winnipeg is 3,000 kilometers, is it exactly 3,000? Or like, was that measured 3,000 kilometers exactly? Or is it about 3,000? Okay, we don't really know. So we know it's close to 3,000, so the 3 is significant, but the other ones aren't. We're just not very confident in that 3,000 meter reading. Okay, so just one sig fig. A number like 0.0058 grams, the zeros are simply placeholders. Okay, if it was 0.00580 grams, okay, I know that's the same amount, but there's actually one more sig fig, okay, because it's a final zero afterwards and it is measured, right? Someone actually found a more precise instrument that could measure to that next decimal place. Okay, adding and subtracting sig figs. Okay. This is going to seem a little bit complicated at first. We're gonna work at adding and subtracting sig figs, and then multiplying and dividing. Okay, let's go up here. So when adding or subtracting measured values, the simple rule is the final answer can't be more precise than the least precise value. Okay, so let's say I'm measuring two things. One I've measured to 5.00 centimeters, and the other one I've measured to 2 centimeters. The 5.00 centimeters, I've measured that to 2 decimal places. This one I only measured to 2 decimal places. So it doesn't make sense to say that the total length is 7.00 centimeters, because I wasn't really sure about this one. It's around 2. It might be 2.00, but probably it's just about that. So my answer, 7.00 centimeters, that's too precise. I don't know if it's exactly 7.00. Okay, so I just have to say it's 7 centimeters. For instance, let's use a bizarre example. We're going to add 2 distances. Okay? The distance from Vancouver to Edmonton is 1,159.6 kilometers. The thickness of human hair is about 0.07 millimeters, or 0.00007 kilometers. Okay? So we have 2 measurements, and we're going to add them together. Okay? Now, when we do that, if I add this and this, then mathematically I get this, 1,159.6007 kilometers. Okay, that is very precise. That is too precise, because I actually don't know the decimals behind the 6 here. Okay, was it exactly 1,159.6? Was it all zeros behind there? I don't know. So my answer can't be that precise, because I'm not entirely sure what the decimal places are behind here. Okay? So that makes our answer much more precise than one of our measured values. How sure were we that the distance to Edmonton was 1,159.60000 kilometers? We weren't. Okay? It might be 0.60003 kilometers, which then makes our final answer 1,159.60010. Okay, so it doesn't make sense to be that precise when we weren't that precise with one of our measurements. Okay, so that's a bizarre example, I get it. So when adding or subtracting measured values, the final value cannot be more precise. So the sum of the 2 distances is accurate to only 1 decimal place. So what we're going to do is we're going to look at, I'm adding these 2. Which one has the fewest decimal places? That's how many decimal places I'm going to use in my final answer. Okay, so I'm left with 1,159.6. I don't know what's past that. So let's use some less bizarre numbers. Add the following. Okay, so we've got those 3 measurements. 14.563, so 3 decimal places there, 12.2, 1 decimal place there, and 0.0005, 4 decimal places. Okay, so I'm going to get a distance, right? I'm adding 3 distances. I'm going to end up with a distance. And I get 26.7635 meters. But this one just had 1 decimal. So my final answer can only have 1 decimal. Okay? So it's 26.7. But then you need to think about, how do I round that off? So that is going to be 26.8 because I have to look at the next decimal place to figure out if I should round it up or down or keep it. Round it up or keep it. Okay, so 26.8. Okay, so mathematically it comes to 26.7635. This one has only 1 decimal place, 12.2. So my final answer can only have 1 decimal place. And I have to round it up in this case to 26.8. Okay. Multiplying or dividing measured amounts. Here we follow a different rule. Okay. Find the area of a rectangle 12.8 centimeters by 13.56 centimeters. Okay. So I'm going to get an area. The units will be centimeters squared. And when I multiply 12.8 and 13.56, I get 173.568. Okay. When I added, I looked at how many decimals. When I'm multiplying or dividing, I look at the sig figs. So this one has 3 sig figs. This one has 4 sig figs. So I have to make this only have 3 sig figs. Okay, it's a different rule when we're multiplying or dividing. I'm not looking at decimal places. I'm looking at sig figs. Okay, so 12.8 has only 3. So my answer can only have 3. So this to 3 sig figs is going to be 174. Okay, so 173.568. 3 sig figs, 173, rounded up to 174. Yeah? So, that was a lot of stuff. There are only 4 rules for sig figs, so I don't think it's too complicated. You guys will get it. You're a bright crew. So, hope that made sense. Have a fabulous day. Take care.